Science.
This is episode 2 of Physics Astronomy Guys. I'm Alan.
And I'm Ian. This is a show about science.
We're going to start off the episode with some current events in science.
Now, our first current event has to do with solar sails. So I'll give you a little background knowledge on solar sails. Solar sails are pretty much giant pieces of aluminum foil flying in space. They're micrometers thick.
And a micrometer is a millionth of a meter, a thousandth of a millimeter.
And these giant aluminum foil ships have just one reflective side, which is basically just aluminum foil. It's propelled by photons, which is given off by the sun. The photon hits the reflective side and pushes it a little bit, because photons have momentum, expressed in the equation P equals E over C, sorry.
Right, and the non-reflective side, it can point towards the sun to fall in towards it, right?
Mm-hmm. And so that brings us to our current event, which is there was a solar sail launched in September by NASA that wasn't working properly or something like that, and it was pretty much dead. But just recently, today, January 19th, 11:30 a.m. Eastern Standard Time, it just spontaneously came back to life, which was good for NASA, and they got confirmation because it deployed one of its satellites.
Now, up until this point, the only known solar sail to have worked was the Japanese solar sail called Icaros, which stands for Interplanetary Kitecraft Accelerated by Radiation of the Sun.
Yeah, that was launched by the Japanese a little ways ago.
Yeah, I think it was launched May 21st of 2010.
Mm-hmm.
It didn't actually do anything. It was just testing the idea.
Yeah, it was just seeing if the solar sail concept works, which it does. And that brings us to our next current event, which is a bit more interesting. Scientists believe that above storm clouds, or thunderstorms, I guess, there are antimatter beams.
So what happens is the storms will emit what are called TGFs, which stands for terrestrial gamma ray flashes. And along with super high energy ions, it will also emit antimatter particles.
Mm-hmm. Scientists think that over 500 of these happen a day.
Okay, so we'll now move on to
our topic of the episode, I guess, which is on Kepler's laws of planetary motion. The first law being the orbit of every planet is an ellipse with the sun at the focus.
So you can imagine an oval. In astronomy, we always call it an ellipse. A lot of people think that planets move in circular orbits, but that's not true. Every planet has a little bit of an eccentricity that makes it actually an oval. And now, at every oval, there are two focal points. Basically, what these focal points are is if you put these 2 points on a whiteboard and then attached a string around them and used a marker and moved it around, it would create the oval that you want.
You can actually try that experiment if you just have a whiteboard, put 2 points, get a string, put the marker over the string, you'll have an ellipse. We promise.
Now, the sun has to be at one of these focal points. So that's the first law.
And the second law is a line joining a planet and the sun sweeps out equal areas of equal times.
And what that basically means is that the closer you are to the sun, the faster the planet has to go. If you think about that, that makes sense, because if you're closer to the sun, you have less gravitational potential energy. And because energy is conserved, that would mean that you would need to have more kinetic energy. If you're farther from the sun, you have less gravitational potential energy, and therefore, and therefore, or you have more gravitational potential energy.
Sorry.
And therefore, you'd have less kinetic energy. Now, basically what it's saying by equal areas and equal times is that you can imagine, although there is a little bit of curvature every second of motion, each second you can imagine a planet moves in pretty much a straight line. So you could take point A and point B and use those 2 points and the sun to create somewhat of a triangle. And basically, what this law is saying is that if you're closer to the sun, you have to move faster so that you get a wider base every second because your height is shorter. So you need a wider base in order to create a triangle with a larger area.
And now for the third and final law, which is a bit more confusing. It's the square of the orbit period of a planet is proportional to the cube of the semi-major axis of its orbit.
So this is probably the most complicated of all of Kepler's laws, but you can explain it in relatively simple terms. Basically what it's saying is that if you are twice as far away from the sun as Earth, you take the cube of the semi-major axis. So if you're twice as far away, cube that, that's 8. That has to equal the square of the year. So now to undo that, you take the square root of that. Square root of 8 is about 2.82. So what that means is that this planet that's twice as far away would take 2.82 years to move around the sun.
And that's all 3 laws. Tell us in the comments below what you would like our next videos to be about, the topics.
We don't have a viewer's choice
question yet.
Video today. Or no, we have a question, just not the topic.
The topic, because the second episode, I guess. So, below, just leave comments if you think the video's too long or too short. Tell us below. We new with this video thing, so just tell us what you guys want.
And now to conclude it, we will give the question of the day, which is this. If the farther away you go from the Earth, the gravity gets less but never reaches 0, why is it that if you fall from infinity, you will only reach a finite speed by the time you get to Earth? So,
good question.
If you can answer that correctly,
you will be recognized as the genius of the episode right there. Maybe. Thank you for watching. Look for our next video some point in time and subscribe and like and put comments below. See ya.
Thanks.